My name is Namiko Saito and I will present a work on real-time liquid pouring motion generation, end-to-end sensorimotor coordination for unknown liquid dynamics trained with deep neural networks. With our system, a robot holds and shakes a bottle as to estimate the liquid characteristics such as viscosity and field level of liquids in it without calculating to find out the parameter of them. Then the robot pours a target amount of the liquid to another container. In many fields, the robots that can handle liquids are demanded. However, they are difficult because unlike solid objects, liquids have characteristics that are complicated and motion-dependent. Even if the goal amount to be poured is the same, different motions are required if the characteristics of the liquids in the container are different. The traditional method for estimating liquid characteristics is the system identification. It identifies parameters of the characteristics using observed data. However, previous studies were limited because the model for estimation of liquids and manipulation was separated. They are also difficult to perform neither with a specific type of liquid nor container in unspecific environments. We propose a liquid pouring model that shapes a dynamical system trained with deep neural networks. The DNN model estimates liquid characteristics and generates a pouring motion sequentially. As for humans, we can shake or touch the containers and perceive the characteristics of the liquids. We take inspiration from human physiology. So, at first, we control the humanoid robots to hold the liquid bottle and shake it to estimate the characteristics. Then, the DNN model generates pouring motion commands. The method is as follows. At first, we guide the robot to do actions and collect data. Then, we train the model to learn liquid characteristics and pouring motions. Finally, we evaluate if the robot can estimate the characteristics and pour certain amount even if the liquids are untrained. This is a learning model. It consists of an image feature extraction module and a sensorimotor module. The image feature extraction module made up by convolutional autoencoder compresses the image data and extracts the 10-dimensional image features. It is important for decreasing the learning cost and generalizing the image data. Then we input the image feature, motor angle data, and force sensor data to the sensorimotor module that is made up by long short-term memory networks, LSTM. It learns to estimate the liquid characteristics and accumulate the information to the internal state. It can also predict the next step sensor-motor data. By control motor commands of the robot according to the prediction, the robot can generate motions. We will show you the result of liquid pouring by the robots in real time. For the evaluation, we passed bottles of untrained amount and viscosity liquid. In this time, I passed 125 grams of medium viscosity liquid made by mixing 2 trained liquids. The aim is to pour 50 grams of them into the saucer. At first, the robot shakes the bottle and estimates the characteristics. After that, the robot itself considers how long and which angle to pour and conducts it in accordance with the liquid characteristics which change in real time. As can be seen, the robot could pour nearly 50 grams. We confirmed that the robot could pour according to the characteristics of the liquid. We tried 3 different viscosity liquids and the robot succeeded all the tasks. We also analyzed the internal value of the Sensorimotor module. We evaluated whether the robot can discriminate the liquid characteristics. This is the result of principal component analysis. The plots are clustered depends on their characteristics, so it can be said that the robot could estimate them well. Thank you for watching.